it's me. Hi, my name is Bilkent. I'm a junior physics student at Bilkent University, and I'm trying to be very quiet right now because basically everyone in my family is asleep right now. Today in this video, I hope to present you with our term project for the Physics 211 course, and I hope you enjoy it. Have you ever wondered why the sky is blue? Well, it has been a topic of debate for millennia. However, supportable theories on the matter have only been able to come up after the introduction of the theory of light by Sir Isaac Newton in the 16th century. However, the most current explanation came in 1869, when the famous Irish physicist John Tyndall discovered a very strange phenomenon while he was cleaning his experimental instruments. He shone a bright light through the purified air he used in his infrared experiments and saw that nanoscopic particles that remained in the air gave off a faint blue tint. He theorized that perhaps a similar effect was at play with the sunlight coming to Earth, and that would cause the blue color of the sky. This theory was furthered by Lord Rayleigh when he published two papers where he related it to the volume and refractive indices of the particles, and was later even able to show that it could also be written in terms of molecular polarizability. This effect, called Rayleigh scattering, was then defined as a type of elastic scattering when a beam of light interacts with a particle much smaller than its own wavelength, which causes the wave to disperse around the particle, which we see as the scattered light. This effect can also be explained in terms of the polarizability, where the incident light causes the particle to become a dipole, emitting radiation that we see as the scattered light. Lord Rayleigh understood that the intensity of the scattered light was inversely proportional to the fourth power of the wavelength. This meant that when you took the visible light spectrum, as you went to the shorter wavelengths, so mostly the blue-green end of the spectrum, you would have a higher intensity of scattering when compared to those of the other end of the spectrum, so the more red and orange wavelengths. This relation then easily explained the blue color of the sky, because as sunlight passed through the atmosphere, mostly the blue wavelengths in the sunlight scattered within the atmosphere, causing the sky to appear blue. This would also explain why we see the sun as sort of yellow and not entirely white, because the unscattered wavelengths that pass through the atmosphere and hit our eyes are a mixture of the green, yellow, and red wavelengths that the sun emanates. However, as the sun gets closer to the horizon, the scattering intensity increases for all wavelengths. This means that even the red end of the spectrum gets scattered. This would explain how, during sunset, the horizon starts to appear more crimson in color. And because the only unscattered wavelengths left is in the far end of the red spectrum, the appearance of the sun becomes more crimson as well. In our experiment, we aimed to replicate this effect in a sodium thiosulfate solution where we added sulfuric acid droplets to form sulfur. We used Lord Rayleigh's equations, where he related the intensity of the scattered light to both the polarizability and the refractive index of the particle. We then plotted the scattering intensities for each wavelength in the visible spectrum based on the theoretical expectations. We both did this for the difference in polarizability of the solution through time and the difference in the refractive index of the solution through time. The results of these graphs can be seen here. From these graphs, we expected the container we had the solution in to turn blue in hue as time went on, and we placed a camera at the other edge of the container to capture the wavelengths that did not scatter. Based on the graphs, we theorized that the wavelengths passing through the container and hitting the camera would grow more red in hue as the intensity of the scattering of the mid-range of the spectrum would increase in time, leaving the only unscattered wavelengths at the far edge of the red spectrum. Once we conducted the experiment itself, we were thrilled to see that our predictions were in fact right. The color of the solution in the container grew more blue in time, while the wavelengths hitting the camera grew more red. However, as we got close to the end of the experiment, we saw that the edge of the container started to gain more red hues as well. This was due to the fact that as the particles in the solution increased, the scattering intensity of the red wavelengths also increased. This is similar to how during a sunset, the sky in the horizon appears to be more red as well. Finally, while we were sufficient with our observational results, we wanted to take things one step further. We took the video from the camera that was pointed towards the container, where most of the red spectrum light hit it, and we tried to find the RGB values and hue values for one specific pixel through time. Once plotted, we saw that the color of these wavelengths, which simulate the sun, went from a yellowish white to a yellow-orange to finally a red-orange, and then ended up in a dark maroon color towards the end of the experiment. All in all, the experiment was a success, and we were so grateful to see that our predictions had come true. Well, I sure hope that you enjoyed the video. I hope you learned something, and I guess I'll see you in the next one. I should really get to bed. I've got demo day tomorrow. Bye.